Hello students, welcome to my lecture series on reinforced concrete structures. In this lecture, I am going to discuss about limit state method, that is conforming to IS 456-2000. The outcomes of today's lecture are like this. On completion of this class, the student will be able to know what is the limit state and its types, and it defines the characteristic strength and the design loads of a material, and importance of partial safety factor used in limit state method and its values as per IS 456-2000. Now we will recap what we discussed or recapitulate what we discussed in our last class. In last class we have discussed about methods of design of RC structures. Generally these are three methods. Those are working stress method, ultimate load method and limit state method. And we have discussed elaborately about the working stress method. This method is based on the stress permissible stresses or permissible values of stresses, and here we calculate the working stress. Based on the working stress we will design the elements, but the designs what you made by using this working stress method are finally we conclude that is uneconomical but safe. Because why it is safe and why it is uneconomical? The structures which are designed based on the working stress method are giving more cross-sectional area. The size of the section is given more, so I can say it is uneconomical. Because of larger section, the structure will be safe. Then next, coming to ultimate load method, this is based on its ultimate load values. This ultimate load values are calculated by enhancing the values of working loads. That means that ultimate load can be calculated by multiplying the working load with some load factor. That is called ultimate load. The structures are the elements which are designed by using this ultimate load method are very economical, but they fail to satisfy the serviceability and durability requirement. Why? The structures which are designed or the elements which are designed by using this method are giving very thinner sections. So thinner section may be able to bend or deflect. Because of its thinner section it may deform. Because of that it is unstable. I can say it will give the unstable structure. Because of a thinner section the usage of material and usage of manpower will be less. Because of that it may be very economical, right? Then to overcome the problems or the drawbacks of these two methods, working stress method and the limit state method, one more method was developed, that is a limit state method. This method is based on the characteristics values, and it is a comprehensive method. That means it can take the drawbacks. That means it can take the working stress, working loads as well as ultimate loads for designing the RC structures. Now in this class we are going to discuss in detail about this limit state method. Generally this limit state method was developed in 1955, but it is implemented in India in 1978. Not fully, partially, but it is fully implemented in India in the year of 2000. So on the year, that's why we got a IS code, that is IS 456-2000 is completely related to the limit state method of RC structures. And this method is advancement over the traditional methods like your working stress method and ultimate load method. And it is a plastic design method. How it is plastic design method? Right. If you take the working stress method, in working stress method we have discussed that the load should be, or the structure should not reach or should not go beyond its elastic limit whatever the loading condition. That means the structures which are designed, that's why the structure designed in working stress method are based on the elastic theory. So that will not reach its go beyond its elastic limit. And if we consider the ultimate load method, we are designing that structures or the elements based on the ultimate load. That means that falls in ultimate region of the stress and curve. Now we are designing the elements of a structure by using limit state method within, above the elastic limit and below the ultimate limit of a material. So that limit or that zone is called a plastic zone. So now we are designing the elements of a structure by considering stresses in a plastic region. So the design made by this limit state method may be a plastic design method. And this limit state method represents comprehensive and a rational solution to the designs. How? Because we are overcoming the shortcomings of this WSM and ULM methods. As I discussed, the WSM, the working stress method, is based on the calculation of working stress of a material only, and the ultimate load method is based on the calculation of ultimate load conditions only. But this limit state method will consider both, that is working stress or the working load and ultimate load also. That's why this method will give comprehensive and rational solutions to the design. Right. What is the concept of this limit state method? What is the concept behind in this limit state method? In this limit state method, consider the safety and serviceability of the structure. Generally, the safety at the ultimate loads and the serviceability of a structure at working load. That means the structure which are designed by using this limit state method or by using ultimate loads, and the checking the serviceability of that particular structure under working loads. So by considering these two parameters like safety and serviceability using in this limit state method, and how to achieve, how can I say my structure is very safe and my structure is serviceable, and how to achieve these two criteria in the limit state method. Right. The safety and serviceability of a structure can be achieved by providing adequate factor of safety and the limit state by considering the limit state. As I discussed, what is that limit state and what is the factor of safety in our last class. Right. So what is the factor of safety means? Example I have given that when you're going for the exam, we'll take 2 pens. Why should we take 2 pens? If anything happened to the first pen, then we can use the second pen. That is, the second pen will be the factor of safety. Right. Then let me discuss what is the limit state. The actual definition of limit state as per IS 456-2000 is the acceptable limit for the safety and serviceability requirements before failure of a structure or before failure occurs in the structure. So what do you mean by this? So if you consider any material or the structural element, and if you apply a load over it, it will going to fail at particular load. If you consider the load which is before failure of the structure, that load will be considered as a limit state of that particular material or particular element. This is how we fix the limit state of a particular element or a particular material. Right? And these limit states are two types. Those are limit state of collapse and limit state of serviceability. This limit state of collapse, which limits of collapse at which the structure is likely to collapse. Right? How we assess the collapse of a structure? When we say the structure is collapsed, if the rupture may happen or ruptures may happen in one or more critical sections of a member, or a buckling may happen in that member, or overturning of structure may taking place. In these situations, we can say the structure is collapsed. So while designing the member, we have to take care of all those things, that is the rupture, buckling and overturn. Right? The limit state of collapse are corresponding to these 4 parameters. Those are flexure. Flexure means a bending, a torsion, shear and compression. Right? Here if I take the beam, I want to design a beam by using a limit state method. Here beam is a flexural member. How it is why I am saying it is a flexural member? Beam is a horizontal member. It is subjected to a vertical loading. When I apply a vertical loading over a beam, it is going to bend. That is nothing but a flexure. If you want to design the beam by using this LSM, then we have to take the conditions, the provisions and values which are recommended in IS 456-2000 in limit state method, that is limit state of collapse in flexure. Similarly, if I want to design a column, as I said, the column is a compression member. They are subjected to a vertical loading, then column going to compress. And this will be designed by using limit state method of collapse, corresponding limit state method of collapse of compression. The assumptions what you made in this condition and this compression condition and assumption what you made in the flexural conditions are maybe different. And the codal provisions given in this condition of a flexure and the codal provision given in this compression conditions are different. Based on those conditions, we will design a column or a beam or any torsional members or any shear members. So that we can, if you use this code or if you use these codal provisions, then we can achieve our safety and serviceability criteria by using this limit state of a collapse. So another state of limit state is serviceability. It will give the performance of the structure at under working load. As I said that we will design the structure by using ultimate load and we will check the performance of the structure based on their working loads. And this serviceability can be assessed under excessive deflection and excessive cracking. Because of the deflection, the deflection will adversely affect the finishes. That means if any structure is subjected to a deflection, then the finishes like plastering may open up or are going to fall. Then the inmates of that structure will feel discomfort. And excessive cracking in the member or a structure will leads to the inefficiency of the structure and it will looks very awkward. And the limit state of serviceability is corresponding to the following parameters, that is deflection, cracking and other limit states like vibration, fire resistance and durability. So we have to check all those things while designing the members by using limit state method. Right. Here I said one of the factors by considering to achieve the safety and serviceability of the structure. One of the thing is by considering a limit state. Another thing is very important thing is that is partial safety factors. The values of partial safety factors are based on experiences and tradition and some engineering researches. Based on those values, we can fix what is the partial safety value, factor value for particular material or particular design of particular load. And the main purpose of partial safety factor is to satisfy the below criteria. What is that criteria is? Design resistance should be greater than design load effect. What do you mean by this? Say, if you take any material, if you apply a load over that, it having resistance to deformation because of that effect of load. That resistance always greater than that design effect or always greater than that effect of the load which is coming onto the structure. Right? These partial safety factors also used to use reducing the material strength by reducing the material strength. Why should we reduce the material strength? That I will explain with the help of this example. The strength of material, say you have chosen one material, the strength of that particular material is say 30 MPa. I am using the partial safety factor of that particular material is 1.5. Right? If I want to reduce the strength of that material, that will give the reduced strength of material is 30 by 1.5, that equal to 20 MPa. Though that material is having capable of resisting 30 MPa of stress, but we are using in design only 20 MPa. Reason is that 10 MPa is as a factor of safety. If in future, because load may vary, load may increase, though the load is increases, that material is having capability of resisting that increased load. That's why we are reducing the actual strength of the material or the actual strength of the member while designing that particular member. And similarly, this factor of safety also used to enhance the load. Why should we enhance the load? Say, I will explain that also with the help of this example. That is, say, after assessing all those loads, the dead loads and live loads or any slow loads, slow loads, you got the design load of that particular member is 50 kilonewtons. Here I am using the partial safety factor of load is 1.5. Then I am enhancing the load, the actual load, by multiplying the factor of safety of 1.5. That is 50 into 1.5 is 75 kilonewtons. Now enhanced design loads are 75 kilonewtons. Here why I enhanced the design load here? If I design a member by using actual design loads, that is 50 kilonewton, I may get a particular cross section. If I design with the enhanced design load, then I will get the more cross section than actual design loads. We know that the more cross section will leads to the more stability of the structure, it having more resisting capacity to the externally applied loads. That's why we are enhancing the design load. So we cannot blindly enhance the load, but there are some rules and regulations, and there are some provision from code. According to that code only, we have to enhance the design load. Right. The partial safety factors for materials generally represented with a gamma m. As we are designing a RCC elements, in RCC elements we are using the materials like concrete and steel. If you want to the representation of those material factor safety is in terms of gamma m, and similarly partial safety factor for loads are represented with a gamma f. Generally those loads are dead loads, live loads and slow loads. While designing the these design loads, we will consider combination of all these loads. On which area we are constructing that particular structure. If it is the structure is constructed in the snowfall area, then we will consider what is the dead load. Generally dead load is our self-weight of this member, and if any live loads are there or not. And definitely as it is a snowfall area, then we will consider snowfall. That means the total design load can be calculated dead load plus live load plus snow load. And what is the enhanced? What is the enhanced design load? That will be calculated from the codal provisions. So for each load there is a separate factor for the separate partial safety factor for the each load. So dead load is separate. For our live load we have a separate partial safety factor. For a slow load, similarly for the earthquake loads. Those were given in our IS 456-2000. From that code we can calculate a total load or total enhanced design load. Right? Here the recommended values of partial safety factors as for IS 456. Thus, if we consider the partial safety factor for a material, generally, so for RC constructions, we are using two type of material, that is steel and concrete. If you are designing your element with respect to limit state of collapse, that is for the steel, we have a partial safety factor is 1.15, for the concrete it is 1.50. And similarly, in terms of limit state of serviceability, then the partial safety factor for the steel is 1 and the partial safety factor is concrete is 1. Right? Here again the question is, we are using a higher partial safety factor value for concrete than the steel. Why? Because steel is a mission made and concrete is a man made. Here mission will have less liable to do the mistakes. And man-made concrete, we have the man-made chances of making more mistake. At the same time, this steel is manufactured on the controlled quality controlled environment, and that's why high degree of quality control is possible there. Here concrete is manufactured or prepared at low degree of environment. Means we are manufacturing concrete in open site. Then the temperature is different, humidity is different, right? And you may have some inferior material, and sometimes we are human beings may mix the concrete in different proportions than they require. So that's why there is a more at the end of the preparation of concrete. If you test the concrete, you may not get the required strength. So that we are using more factor of safety for the concrete than the steel. This accounts for the following parameters. Just what I discussed here. There is a possibility of deviation of strength of the material. Yes. a deviation of sectional dimensions, and accuracy of calculation of procedure are a risk of a life and economic consequences. As I discussed earlier, all those points will comes. All those things are comes under all these 4 points, right? And the recommended partial safety factor values for the loads. As I said, we are using the combination of loads. We cannot use single load. We cannot design the structure by considering alone dead load, because we may have some live loads on them. We may have the wind effect on that particular structure. We may have some earthquake loads, or we may have designing that load, or constructing the structure in snowfall area. So based on the combination of loads we can use here, right? If you take the combination, or if you take a combination of loads here, dead load and live load, dead load and wind load, dead load and wind load and live load, these are the combinations. And if you take we are designing the structure in limit state of collapse, then the factor of safety for the loads for the dead load is 1.5, for the live load is 1.5, and for the wind load is 1. And similarly, for if you are using the combination of dead load and wind load, then you have to use dead load factor of safety is 0.5 and wind load factor of safety is 1.5. And if you are using this, designing the structure by using dead load and wind load and live load, then the factor of safety in limit state of collapse for this load is 1.2, 1.2, 1.3. And similarly, in the case of limit state of serviceability, here if you are using combination of dead load and live load, the limit state of serviceability criteria should be taken that partial safety factor for dead load is 1, live load is 1. Similarly, for you are taking combination of dead load and wind load, then for you are taking for the dead load, it is the partial factor safety is 1, for the wind load it is 1. And if you are taking combination of all these loads like dead load, wind load and live load, then the partial factor safety will be like this. That is, for dead load in a limit state of serviceability, for the dead load that is 1, for wind load that is 0.8, and for the live load that is 0.8. So the reason for providing the partial safety factor in load is because of these reasons. That is, unusual increasing load may take place during its service, and unforeseen stress distribution may take place, and we may inaccurately assess the effect of loading while designing the structure. To overcome all this problem, these partial safety factor are used so that we can design a serviceable and safe structure. Right, now we'll discuss what are the characteristics values and characteristics loads. So characteristics values are a characteristic strength of a material and a characteristic load of a material. Right, as I discussed already in our last classes, what is the characteristic strength of a material? It is the value of strength of the material below which not more than 5% of test results are expected to fall. That means if you take 100 sample, in that there may be a given tolerance that maybe 5% of test results may fail, and remaining 95% of test results must pass to calculate the characteristic strength of a particular material. Similarly, we can define what is the characteristic strength of a concrete. It is the compressive strength of a concrete of 150 mm cube at 28 days of curing in Newton per mm square. So below which not more than 5% of test results are expected to fall. That means during the compression test on a cube at laboratory, not more than 5 in 100 cubes will fall below the actual required strength of a cube. That is what the characteristic strength of a concrete. Generally, it is denoted with a FCK. Next, a characteristic for the steel. If I want to define what is the characteristic strength of a steel, it is minimum corresponding to the minimum yield point or minimum yield strength at 0.2% proof strength. What do you mean by this? Here if you take a mild steel, the stress strain curve of a mild steel will be like this. This is proportionality limit, elastic limit, upper yield point, lower yield point, ultimate point and breaking point. So for a mild steel rod, if you want to define the compressive strength of that particular mild steel, that is defined as a minimum yield strength. What do you mean by minimum yield strength? That the strength of the steel corresponding to the yield point. Which yield point? Generally we consider the strength of that mild steel rod corresponding to the lower yield point. So here Y2 in this graph, Y2 is the lower yield point, Y1 is the upper yield point. The strength corresponding to this lower yield point is considered as a characteristic yield strength of a mild steel, right? If you take a HYSD bars, if you conduct the tension test on that, if you draw the stress strain curve of that particular HYSD bars, you will not get a definite yield points for those HYSD bars. So we are not considering, if we are not getting the definite yield point for the HYSD bar, then how to calculate its yield strength? For HYSD bars, the yield strength can be calculated corresponding to the 0.2% of a strain. That is called, the strength corresponding to the 0.2% of strain is called 0.2% proof strength. So here I will take a graph from IS 456-2000. This is the strain and the stress for HYSD bars or high yield strength bars. Here we have a 0.002, means it is a 0.2% of strain. If I draw a parallel line to this actual graph, this graph, and it will intersect on this graph here. So this line represents the line corresponding to the 0.002 strain or 0.2 strain, 2% strain, right? If I calculate the stress corresponding or the strength corresponding to this strain, I will get a strength, that is Fy here, that is Fy is a yield strength of HYSD bars. This is also called calculating of this 0.2% of proof strength, also called, this method is called offset method, we can say. That is, it is the offset from the origin of the graph. I am repeating, the minimum yield strength, the characteristic strength of a steel, one is corresponding to the minimum yield strength, another is 0.2% proof strength. This minimum yield strength can be calculated with respect to the minimum yield point or lower yield point of the stress strain curve, and for HYSD bars the 0.2 proof strength, I can say, this can be calculated with respect to the 0.2% of a strain, right? I think it is clear. The characteristic value should be based on the statistical data if available. If data is not available, based on the experience, we can calculate the characteristics values. Then what is the characteristic load? The characteristic load means it is that value of the load which has 95% of probability of not being exceeded during the life of the structure. So what do you mean by this? Here the load that is estimated at the time of design of a structure is at any time during the life of the structure, the estimated value, the load is more than that estimated value, should not exceed 95% probability. That means it has only 5% of chances to exceed that estimated load throughout its life of the structure. So that is the meaning of that characteristic load. So generally these design values are derived from the characteristic values through the use of partial safety factors. That means design strength of a material can be calculated using this formula, that is characteristic strength per factor of safety of a material, partial factor of safety of a material, and design load is equal to the characteristic load multiplied by factor of safety of that particular load. So that's all about today's presentation, and we have some questions here which are previously asked in the various competitive examinations on today's topic. The first question is, which of the following method gives stable and economical structures? Option A, working stress method. Ultimate B, ultimate load method. C, limit state method. C, none of the above. So we know that by working stress method we get the structure stable but uneconomical. By using limit state method, economical but unstable. By using limit state method, we'll get both economical as well as stable structure. So the answer is C. By using limit state method, we get stable and economical structures. Right. The second question is the partial safety factor for steel in limit state of collapse as per IS 456-2000 is. Here, as per limit state of collapse, by using IS 456-2000, that the codal value is the partial safety factor for steel is 1.15. So the option D is correct. The next question asked is the limit state of serviceability is corresponding to flexure, torsion, shear, all the above. So limit state of serviceability is corresponding to all the above. In addition to all these things, those are flexure, torsion, shear, we have compression also. So the answer is D for this question. So thank you. That's all for today's presentation.